For our entire existence, humans have asked the same basic question. Why are we here? Where did we come from? What created us? From the great ancients to the Renaissance masters, and finally to the modern giants, humans have made more progress answering that question. The answer is completely tied to how the universe works, and modern astronomers are working on the foundations of our past and using new technologies to answer more and more complex questions about the origin of the universe. One of the very first arguments had over the origin of the universe was the finiteness of the past. Noted Greek philosopher Aristotle, who also came up with one of the earliest popular models of our solar system, posed that the universe has an infinite past. This belief appeared to be the standard for many centuries, until thousands of years later, Abrahamic philosophers couldn't reconcile an infinite past with their theories of creation.
The first recorded and decent theory of the beginning came from medieval English theologian Robert Grosseteste. He depicted the birth of the universe as an explosion of matter, which then crystallized into the Earth and a set of concentric spheres around it. It was the first attempt to describe the origin of the cosmos with a set of constant physical laws. While still not completely accurate, it was a good start. Other key figures arguing for a finite universal past included Johannes Kepler and Sir Isaac Newton. It's pretty obvious that humans have been trying to figure this out since the beginning. I mean, it's the most obvious question, right? The problem with a lot of these theories, though, is that they're more religious or superstitious than they are physical or scientific. You know, like, I don't know, you can name any civilization and they've got a creation story, but it's always something wacky. If you go to, like, the ancient Egyptians, they said that, you know, the universe was just an endless sea of water with no light, and then this god, the sun god Aten, created itself and then just created the world. And so, you know, it's always been answered, but it's been answered wrong. And now we finally are able to use science and observational studies, and we can actually go back to a negligible amount of time after the Big Bang and know what happened.
But first, the Big Bang itself. What is the Big Bang? Currently, it's our best guess at how the universe began. Approximately 14 billion years ago, the universe didn't exist. Space and time were nothing, but suddenly something happened. At this time, the entire universe was one singularity, or point of zero volume and infinite density. Suddenly, it began to expand extremely rapidly, scattering space, radiation, and eventually matter throughout. That much is slightly uncertain, but we do know fairly accurately what happened starting after 10 to the negative 43 seconds. That's a decimal within 42 zeros after the decimal point.
We've mostly got it figured out at this point. We're only missing one or two pieces. The problem is they're pretty big pieces. If you ever hear scientists talk about the unified theory or the theory of everything, that's what it is. So at the very beginning of the universe, all of the fundamental forces, as we call them, were unified into one. And so far, we've been able to link all of them except gravity to each other. And so the unified theory, or the theory of everything, is what links gravity to the other forces, and it's the biggest challenge for modern physicists today, but we've almost got it. I think that should come.
The evolution of the universe is divided into 3 eras, further divided into several epochs each. The epochs of the first era of the universe were determined by separation of the fundamental forces. In the universe today, there are 4 fundamental forces that control everything: electromagnetic force, the strong and weak nuclear forces, and gravity. At the very beginning, all of these forces were unified into one, working as a single comprehensive force. As the universe began to expand and cool, the forces eventually separated from each other and began to act independently of each other. So far, we have been able to relate all of them to each other except for gravity. The unification of gravity to the others is what we mean when we say the theory of everything. The first 10 to the negative 43 seconds of the universe that we don't know about were the time when gravity was unified with the other forces. Let's talk about the first era, the radiation era. The radiation era lasted for roughly 50,000 years, beginning at the instant of the Big Bang. But before going through all of this, it's important to note that mass and energy are different forms of the same thing. So when we say that the universe is dominated by something, we mean that the majority of mass energy in the universe is in that form. The radiation era of the universe was when the universe was dominated by radiation.
It can be pretty hard to understand, but yeah, mass and energy, they're the same thing. You know, it's kind of like how space and time are the same thing, where it doesn't really make intuitive sense, but You just kind of have to accept it as true because without it, physics doesn't really work right. So just keep in mind that mass and energy are the same thing. The Grand Unified Theory epoch is the furthest back that our understanding of physics and the universe allow us to look at it. And it was another incredibly short period, much like the ones before and after it, and the temperature of the universe declined by a fair amount right up until the strong force froze out.
At the beginning of the Grand Unification era, the temperature of the universe was 10 to the negative 32 Kelvin. That's over 1 billion billion billion. There was so much energy everywhere that all the forces but gravity were able to act as one. However, the rapid expansion of the universe allowed for compression and density, and therefore the energy density of the universe to go down, causing rapid cooling. Lasting until 10 to the negative 35th seconds after the Big Bang, the Gut epoch is the second shortest, and saw the universe cool to about 10 to the 27th Kelvin before the strong nuclear force froze out. The next era is the one that laid the foundations for the universe as we know it today, the Quark era.
The quark epoch is definitely one of the more important ones of the radiation era because this is where the atomic building blocks of all matter in the universe began to form. There's so much energy flying around, and now that the strong nuclear force is an independent actor, we can actually see quarks merge together, and the creation of the first protons and neutrons happens. And it's still, like the others, really short, but it was enough time for a lot to happen.
Lasting from 10 to the negative 35 to 10 to the negative 4 seconds, the quark epoch was named for the quarks that were merging within. After the freeze-out of the strong nuclear force, protons and neutrons were formed. Energy can be converted into pairs of matter and antimatter particles, according to E equals mc squared. The universe was filled with a plasma made of quarks, leptons, and their antiparticles, ready to be formed into nuclei or dispersed. At some point in the universe, matter came to dominate antimatter. Next, the lepton epoch began. The lepton epoch was a time period where the universe was mostly only forming leptons, which can form electrons, neutrinos, and other types of particles. This is because the temperature was still high enough to form them, but not most other matter. The most important thing that happened during it was the neutrino decoupling, where neutrinos lost nearly all of their ability to interact with other matter. At the end of this time period, there were enough electrons left behind to keep the universe at a neutral charge.
At this point, there was no longer enough energy to create protons or neutrons, but electrons were being created and destroyed all over the place with lepton and energy activity. So after about 100 seconds at the end of this epoch, there were just the right amount of electrons to cause an equilibrium and cancel the charge of the protons, giving the universe a neutral charge overall.
With the end of the lepton epoch came the nuclear epoch. The temperature of the universe fell below 1 billion Kelvin, and atomic nuclei began to form when protons and neutrons fused together. It's the longest epoch of the radiation era, lasting for 50,000 years minus 10 seconds. But most of the hydrogen and helium in the universe was formed within the first 15 minutes or so.
And thus ends the radiation era. After about 50,000 years, it became matter's turn to dominate the universe. Keep in mind that not all of the forces have been frozen off yet. And at this point, the universe has all the matter it's going to have, and eventually radiation is going to recede, and there will be more matter than radiation in the universe. So this era is divided into some much longer epochs, one of which is actually shared with the era that comes after it.
The first epoch of the matter era is the atomic epoch. This marks the point where matter took precedence in the universe, beating radiation. An important event occurring at the time was the decoupling of electromagnetic radiation, meaning that all of the fundamental forces were finally independent of each other. The other significant occurrence was the appearance of the cosmic microwave background, which has been very important to our studies today.
The atomic epoch was really when the universe began to take on some of the characteristics it has today. It finally became transparent after being an opaque fog for however many thousands and thousands of years, and more importantly, the cosmic microwave background appeared. The cosmic microwave background, we call it the CMB, is something you can kind of think of it as an afterglow of the Big Bang. It's completely consistent throughout the whole observable universe and was one of the two very important pieces of evidence for the expanding universe and the Big Bang theory. It was actually discovered by accident. There were a couple of guys in Bell Labs that they were trying to make an antenna, and they found some weird radiation they couldn't account for, and they ended up winning a Nobel Prize in physics for it.
And so, the stage was set for the universe as it is today. There was radiation, abundant supplies of light elements, and a decent amount of energy flying around, with the average temperature of the universe being 60 Kelvin. 200 million years after the Big Bang, the galactic era begins. It ushers in a period of vast and ambitious formation of large structures, like galaxies and clusters. This epoch is not always named, but the time period is generally agreed upon. Following the galactic epoch is the current time period, the stellar epoch.
Right now, today, we're in the middle of the stellar epoch. Maybe not the exact middle, but the time scale of these, it's so large that we might as well be in human terms. This is the time period where most of the stars in the universe are going to form, and it only goes downhill from here. There were some stars that formed before the stellar epoch, but this is the peak of star formation activity. Galaxies are going to evolve and interact with each other still, but they've all pretty much been formed up to this point, and stars are going to be shining all over the place. But during this time period, a fundamental change will occur, which is the domination of dark energy. Now, that's a fun phrase, and it's also the only epoch that is shared by more than one era so far.
While we are still in the stellar epoch, which began during the matter era, we have crossed over into the dark energy era. There is no set end date on it. It is the time period where dark energy dominates the universe, slowly pulling it apart. From this point forward, little can be known about the fate of the universe, and most is left up to conjecture.
And then we get to the end of the universe. It's not pleasant, and I should start off by saying that the timescales are incomprehensibly vast here. We don't really know the exact fate of the universe. We just can't tell for sure. We've got all kinds of ideas, but that's all they are. What's most likely to happen is that the universe is going to continue expanding forever, and everything is going to become isolated from everything else. Galaxies should be able to stay together and everything smaller than that, but eventually it'll just be a bunch of lonely galaxies floating in the middle of space where they can't even see anything else. And at the same time, all of the heat energy in the universe is going to dissipate, so the universe will reach a state of absolute zero, where all molecular motion and therefore time itself stops. And after that, well, we can't really say, first of all, because after isn't really a concept, and secondly, who knows? It could be anything.
The end of the universe cannot be known until it happens, and humans will not live to see it. Statistically, our entire existence as a species will fall well within the stellar epoch, when the universe is relatively lush and fertile for life.